Okay, let's dive right into what is basically the ultimate cosmic detective story. We are tracking down a dormant monster from the absolute dawn of the universe. Picture this. We're looking out into the pitch black void of deep space, trying to find a suspect that literally does not want to be found. It's a mystery that is pushing the absolute limits of modern astrophysics, and it is a wild ride.
So here's an impossible paradox for you. How exactly do you measure the mass of something that is completely invisible? We are talking about an object emitting absolutely zero light, no radio waves, no X-rays, and it's hiding out in the cosmos over 10 billion light years away from our telescopes. You wouldn't even know where to begin placing this scale, right?
Now, to wrap our heads around why this is so wildly difficult, we kind of have to look at how supermassive black holes behave. We can easily spot active black holes because they shine fiercely as quasars. They are messy eaters, aggressively devouring surrounding gas and creating these massive accretion disks that outshine entire galaxies. They're basically the cosmic equivalent of a glowing neon sign. But dormant ones, well, they're utterly silent. They've run out of food, they've stopped feeding, and they pull off the universe's greatest hiding act. Finding one is incredibly difficult, and actually weighing it, that's long been considered practically impossible.
Part 1. Finding the Invisible Giant.
So, astronomers locked onto a massive target, a galaxy designated MRG-M0138. And what makes this particular galaxy so fascinating is its age and its status. We are observing this galaxy from a time when the universe was only 3 billion years old. That's a mere fraction of its current age. And mysteriously, its status is quenched, meaning it's effectively dead. In an era where galaxies were typically just vibrant and bursting with new star birth, this massive galaxy had just shut down entirely.
Part 2. A cosmic magnifying glass.
To actually see into the heart of this dead galaxy, the James Webb Space Telescope needed a cheat code, and the universe provided one: gravitational lensing. Because of Einstein's theory of general relativity, we know that massive objects warp the actual fabric of space-time around them. In this case, a massive foreground cluster of galaxies happens to set perfectly between us and our target. It acts as a giant magnifying glass. It bends the passing light, stretches the distant galaxy's image, and ultimately amplifies it 30 times over. It literally turns JWST into a high-powered cosmic microscope.
Which brings us to Part 3. Watching the stars dance.
You know, if you literally can't see the black hole itself, you have to look at what its gravity is doing to everything around it. By watching the frantic dance of stars near the galactic center using JWST's near-infrared spectrograph, astronomers can actually measure their rapid velocity. Think about it like holding on to a spinning cosmic merry-go-round. The faster it spins, the more massive the anchor at the center has to be to keep everything from just flying apart. By running that complex orbital math, they can pinpoint the immense gravitational pull of the hidden object. Actually, to put this into perspective, the sheer leap in scale here is what makes this such a massive breakthrough. This stellar dynamics technique, it's exactly how astronomers won the Nobel Prize for weighing the black hole at the center of our own Milky Way. But previously, the distance record for pulling this off was strictly in our local cosmic backyard, about 700 million light-years away. With this observation, we just jumped to weighing a dormant black hole more than 10 billion light-years away. It is an absolute triumph of modern observational astronomy.
Part 4. 6 billion solar masses.
So, when the team finally crunched the numbers, the results were absolutely staggering. They discovered an invisible giant weighing an unfathomable 6 billion times the mass of our sun. 6 billion solar masses. I mean, it's almost impossible to wrap your head around a single invisible point in space holding that much weight, especially that early in the history of the universe. That's staggering weight? That's the smoking gun right there. It tells us that early in the universe, this now dormant black hole underwent a period of incredibly rapid, violent growth. It was definitely a powerful, luminous quasar in its past. During that violent feeding frenzy, the black hole released enormous amounts of energy, literally blowing away and ejecting all the star-forming gas right out of the galaxy. By starving the galaxy of the fuel it needed to birth new stars, the black hole forced its host to abruptly die out and become quenched. It essentially ate itself out of house and home, and then it just went to sleep. Which leads us to Part 5, the galaxy evolution mystery. For a long time, we've known about something called the M-sigma relation in the local universe. It sounds complicated, but it's basically a tight correlation, a strict rule showing that the mass of a central supermassive black hole is directly linked to the speed of the stars in the galaxy's central bulge.
It implies that black holes and their host galaxies don't just, happen to exist near each other. They completely co-evolve and regulate each other's growth. But the big question has always been, when did this start? Well, the answer is in. The rule holds true. This new JWST data proves that this intimate coevolution wasn't some modern development taking shape over the long history of the cosmos. No, this complex relationship was already firmly established, totally locked in place, in the universe's infancy more than 10 billion years ago. The black hole in MRGM 0138 perfectly matches the expected mass for its galaxy size, even way back then. Andrew Newman, who led this research over at Carnegie Science, really hit the nail on the head here. He points out that breaking the distance barrier on this technique opens an entirely new window into the early cosmos. They took a tool that we thought was completely restricted to our local neighborhood, and they proved we can use it to map the gravitational ghosts of the distant, distant past. So what is the ultimate takeaway for us? We have finally unlocked the ability to weigh the quiet, invisible giants of the early universe. And the most exciting part? We are literally just getting started. With next-generation observatories like the Roman Space Telescope, Euclid, and the Giant Magellan Telescope about to map thousands of new gravitational lenses, the cosmic dark is about to get a whole lot brighter. I mean, how many more impossible cosmic giants are out there, just waiting to be weighed? Definitely keep that in mind the next time you look up at the night sky. Thanks for joining me on this explainer, and as always, keep questioning the universe.